Okay, welcome dear friends. Am I audible to you? Okay, thank you, Tejas. Sorry for the mistake I made in scheduling the lecture. We will be continuing with our discussion on Exergy. And if you remember yesterday, I had, with the help of some illustrative figures, explained you that there is a decrease in available energy when the heat is transferred through a finite temperature difference. Okay, so the plan of today's lecture is I will be doing that derivation, and if possible, if time permits, you would take a numerical based on that. Okay, so this is the plan of today's lecture. So as I said, we would be deriving an expression for decrease in available energy. So let me write down this. So I am going to derive you an expression for decrease in available energy in case of irreversible heat transfer. In case of irreversible heat transfer, or in other words, if the heat is transferred through, if the heat is transferred through the finite temperature, heat is transferred through finite temperature difference. Okay, this is what we are going. It's very simple proof. You need not worry about that much. Okay. So let us say that there is a heat Q which is to be transferred. Consider that the source is at a temperature. Source is at a temperature of T. Okay, and the dead state temperature is T naught. Dead state temperature is T naught. Okay, so this is, let us say, the source temperature is T and dead state temperature is T naught, and the heat transferred is Q. Heat transferred is Q. Okay. Q. Okay. So we are to figure out what would happen to the exergy of this. Okay. When the heat has been transferred through a finite temperature. So first we need to find out what is the exergy of the. We need to find out what is the exergy or available energy, right, of this heat, of this heat right, at temperature T, heat which is available at temperature T. So you know that this can be calculated as efficiency of the Carnot engine operating between the source temperature T and the dead state temperature T naught into Q, okay, which is equal to 1 minus P naught by T into Q, which is equal to Q minus Q by T into T naught, which is equal to Q minus T naught delta S. Okay. So this is the exergy of the heat which is available at T. Available at T. Okay. Now, how much is this Q? Okay, how much is this Q in terms of temperature and is this Q? So this Q is nothing but the area under the temperature entropy diagram. Okay, when the heat transfer happens. Okay, so this is equal to, this will be equal to P into delta S. This is P into delta S. Okay. So now we have two expressions, that Q is P into delta S, and we also know that exergy of this Q, which is available at T, is Q minus T naught delta S. Q minus T naught delta S. Okay. Now let us assume that this heat is transferred, right? And we are now interested in knowing what happens to the exergy when this heat, which is transferred to through a finite temperature. Okay. So what we would be doing is, now we would be considering the heat transfer Q, okay, through to a lower temperature, lower temperature T dash, such that T minus T dash is finite value. Okay, it is not infinitesimally small. It is a finite value. Okay, so we are now talking about the heat transfer to a lower temperature T dash. Okay, to a lower temperature T dash. Okay, so if you want to represent this process on a temperature entropy diagram, okay, so first we had talked about the heat transfer, okay, from the source. So this representation from the red line, this representation which is in red, okay, this gives you, because the significance of temperature entropy diagram is what? It gives you the heat transfer. So the Q is equal to P into delta S. Okay, Q into delta S. Now your Q remains the same. Q remains the same because there is no heat loss. Remains the same. Why Q remains the same? Because no heat loss. But now this heat Q is now available at a lower temperature. Okay, it is available at a lower temperature. So it means that this Q is equal to P into delta S has to be equal to P dash into delta S dash. Okay, where you know for sure that this T dash, I will show the T dash in green. Okay, this T dash has to be lower than this. So T dash is the temperature. T dash is a temperature which is lower than T, and such that T minus T dash is a finite value. Now we don't know what is delta S dash. Whether this delta S dash is less than delta S, we know for sure. Okay, let me write down. We know for sure that T dash is less than T. This is what we had assumed, that heat is transferred to a lower temperature. So we know for sure that T dash is less than T, but we don't know about delta S dash. So what is the relationship between delta S dash and delta S? That we don't know. Okay, whether it is equal to, whether it is less than, whether it is greater than. Now, if we look at the expressions 1 and 2, if you look at the expressions 1 and 2, since there is no heat loss, so just compare equations 1, 2, and 3. So from equations 1, 2, and 3, okay, mathematically, look at it mathematically. Look at the expressions 1, 2, and 3 mathematically. It would be obvious to you that delta S dash if has to be greater than delta S. Is this clear or not clear? Whether this is clear or not clear, that delta S dash has to be greater than delta S if T dash is less than T. Whether this is clear to you? Yes or no? Okay, Garge is saying yes. Let me see. Okay, Tejas is saying yes. Ganesh, for Ganesh, it is not clear. Kunal is saying yes. Okay, let me repeat it for Trevor is saying yes. Chinmay is saying yes. Okay, so let me repeat it for Ganesh and others who are not followed. Okay, Ganesh, listen. See what we are talking about. We are talking about the heat transfer Q. Heat transfer Q. Heat is being transferred from the source. Heat is being transferred from the source, which is at a temperature of T. Which is at a temperature of T. Okay. So let me go to the previous slide. So when this heat is transferred from the source, which is at a temperature T, and the dead state temperature is T naught, okay, then the heat transferred would be T into delta S, okay, T into delta S. So if I want to represent this process, so the process can be represented as this, okay. This is the heat transferred from the source. This is the heat transferred from the source, okay. So T into delta S is the heat transfer from the source, right? And we had calculated what is the, so heat transfer value is the area of this, and what is the area under the TS diagram, and what is the value of available energy? The value of available energy would be Q minus the T naught delta S, Q minus T naught delta S. Okay, how would we calculate that? By multiplying the Q with the maximum efficiency, that is the Carnot efficiency, with the Carnot engine operating between the temperature T and temperature T naught. Okay. So if you solve this expression, you will get Q minus T naught into Q by T. So Q minus T naught delta X. So this is the Exergy value. Now this Q, which is being transferred from the source, okay, which is being transferred from the source, it is accepted by the working fluid. Okay, it is accepted by the working fluid, and this working fluid is at a temperature T dash, which is lower than the source temperature, and this T minus T dash is a finite value. It is not infinite, extremely small. It is a finite value. So what is the meaning of this? The meaning is, because this is finite value, the heat transfer from the source to the working fluid is an irreversible heat transfer. It is an irreversible heat transfer, right? Now, what would be Q now? The Q would be T dash into some delta S dash, T dash into delta S dash, right? But Q is also T into delta S. Q is also T into delta S, right? Now, if you look at these expressions, expression 1 and 2, so expression 1 is Q is equal to T into delta S. Why is that so? That is the significance of temperature entropy diagram. That is the area under the temperature entropy diagram gives you the heat transfer. Okay. So Q is equal to T into delta S is equation 1. Q is equal to T dash into delta S dash is equation 2. And we know that T dash is less than T. So look at it mathematically, 1, 2, and 3. If you look at it mathematically, it becomes obvious to you that delta S dash has to be greater than delta S. Delta S dash has to be greater than delta H. Yes, okay. So Ganesh, is this clear to you now? Ganesh, correct? Others are saying yes. Ganesh, is this clear now? Okay, thank you, Ganesh. So now it is clear that delta S dash is greater than delta S. Okay, right. So now from the diagrammatic perspective, so obviously your diagram becomes like this. This is the heat transfer. I have represented the heat transfer. Okay. So this green line, this green rectangle, what does that represent? That green rectangle represents the heat transfer Q. Green rectangle represents the heat transfer Q. Okay, now let me again use the red pen. So let me show you with delta S and delta S dash. So this is delta S, let us say. This is delta S, and let me show you delta S dash. So this would be delta S dash. Okay. Now this is about heat. Now what happens to the exergy? Okay. So let us now calculate the exergy of the working fluid because of which is at T. Okay. The exergy of the working fluid now would be. So let me write down that exergy value. So exergy of the working fluid which has accepted the heat Q at temperature T dash would be obviously the efficiency of the Carnot engine operating between T dash and dead state temperature into the heat transfer Q. So this is equal to 1 minus TL, that is T naught upon T dash, 1 minus T naught upon T dash, okay, into Q, which is equal to Q minus T naught Q by T dash. Okay, but what is Q by T dash? It is delta S dash. So it is Q minus T naught delta S dash. Q minus T naught delta S dash. Okay. So if you look at these two expressions, that is the exergy Q minus T naught delta S and the exergy Q minus T naught delta S dash. Okay, you compare the exergy of that is Q minus T naught delta S with Q minus T naught delta S dash. So what do you find from that, from the comparison? Okay, if you compare the exergy, let me write down the exergy here with red. The exergy value, okay, the exergy value, let me put it somewhere here. And next slide. So if you compare the exergy value, which is the exergy of heat when it is available at T, is what? Q minus T naught delta S. Okay, and when this heat is transferred through a finite temperature difference, and when it reaches a temperature T dash, that exergy value is Q minus T naught delta S dash. Okay, and you have figured out that delta S dash is greater than delta S. So what do you conclude from this equation A, B, and equation C? What do you conclude from equations A, B, and C? What do you conclude? Any answers? What do you conclude from equations A, B, and C? Right, Sharvari, you are right. T dash is greater than T, Gargi. T dash is not greater than T. T dash is less than T, Gargi. Anybody, any answers? What do you conclude from this? Sharvari has written it correctly. Exergy at T, yes, correct. Neha, it is correct. Any more? Sharvari and Neha have got it right. Anybody else? What has happened? Right. Correct. Exergy would reduce, okay, decrease. So why is the exergy reduced? Okay, if you look at this, now let me Let me represent the Exergy value. Okay, let me represent the Exergy value on a temperature entropy diagram. Okay, I would be representing this Exergy value on the temperature entropy diagram. Okay. So this, let us say A to B. This area under A to B is what? Area under A to B is what? What is area under A to B? What is area under A to B? They just, what is area under A to B? Yeah, correct. No. Area under A to B is not delta S, sorry. Area under A to B is the heat transfer. That it is correct. Tanaya, it is correct, right? So area under A to B is the heat transfer. Okay. Now, what is area under C to D? What is area under C to D? What is area under C to D? Correct. Gargi, it is correct. What is area under C to D? Aniket, no, it is not delta S. Tanya, it is right. Aniket Kapote, it is wrong. Sharvari, it is right. Tanaya, Sharvari, Gargi, you are right. Aniket, it is not delta S. Area under C to D. So area under C to D is the unavailable energy. Gunjan, you are right. Raju, you are right. So the area under C to D is unavailable energy. Okay. So you look at this. So what is the area ABCD? What is the area ABCD? Area ABCD. Yes, right, Gargi. What is the area ABCD? Right. Neha, you are right. Tanya, yes. Gunjan, right. Girls are smarter. What about boys? Raju, yes, right. Area under C to D, area under, area ABCD is the available energy. Pages, we are right. So now we now we were talking about the heat transfer. So let me draw with the green now. Okay. So green. So now this heat which was Q, okay, is transferred to the working fluid, which is now at a temperature T dash, Okay, so it means that this heat which was there is now getting transferred to a working fluid which is at a temperature T dash. It is an irreversible heat transfer because the temperature difference between T and T dash is finite. Okay, so we had shown that this is a new diagram. Okay, this is the new diagram. So let me use some notations here. So A dash, B dash, A dash, B dash, C dash, D. So what is area under A dash, B dash? Let me ask you. What is area under A dash, B dash? What is area under A dash, B dash? Okay, correct, Garvin. What is area under A dash, B dash? Anybody else? Apart from the usual students who answer. What is the area under A dash, B dash? Gargi is right. Tanaya is right. Gargi is right. Available energy of second heat. It is not second heat, Kunal. It is the available energy of the same heat which has now reached a temperature T dash. Kunal, are you getting the point? It is the available energy of the same heat Q which has now reached, okay, which has now reached a temperature T dash. Means there is no heat loss. Mind well, there is no heat loss, but the heat has reached to a lower temperature T dash. So when the heat has reached to a lower temperature T dash, we are trying to show that the available energy decreases. Okay, the available energy decreases. That is what we are trying to show here. Okay, so it is not available energy. It is area under A dash B dash is not available energy for sure. It is the heat transfer. Okay, it is the heat transfer. So area under, so we need to draw actually area under A to B has to be equal to, it has to be drawn in a manner such that is geometrically correct. If you want to draw this diagram, then you need to draw it like this way. Area under A to B has to be equal to area under A dash B dash, which has to be equal to Q, which has to be equal to Q, and which has to be equal to area of a rectangle, which is nothing but T into delta S, or T dash into delta S dash. Okay, right? Now what is the area under C dash D? What is the area under C dash D? C dash D, mind well. What is the area under C dash D? What is the area under C dash D? Right. Unavailable energy of what? It is the unavailable energy of the heat which is at T dash and not at T. Mind well. Mind well. It is the unavailable energy which of the heat which was at T dash and not, yes, correct. It is at T dash and not at T. Okay. So what is now the area? What is now the area A dash, B dash, C dash, D? What is now the area A dash, B dash, C dash, D? So you see here that area ABCD is the available energy when the heat was at T. Okay, and area A dash, B dash, C dash, D is the available energy when the heat is at T dash. Okay, so what has happened to available energy? What has happened to available energy? So if you draw the geometrically correct figure, you can figure out that the available energy, has decreased. Okay, it is not remained the same. It has decreased. And by how much it has decreased? It is not the same category. The available energy has decreased. Okay, don't look at the geometry and conclude. Don't look at the geometry and conclude. That is having some problem with my pen. Available energy has decreased from, look at this, available energy has decreased from available energy minus available energy dash, okay. Decrease in available energy would be available energy at T minus available energy at T dash. And what is the available energy at T? So look at it now. It is Q minus T naught into delta S minus available energy at T dash is what? It is Q minus T naught into delta S dash. Okay. So if you do the subtraction, if you do the get the difference, then what you'll get is the loss in available energy, which would be equal to T naught delta S dash minus delta S. That would be the loss in the available energy, or decrease in the available energy, or exergy destruction. Is this clear? Whether this expression is clear, decrease in available energy is equal to T naught into delta S dash minus delta S. Is this clear? Whether this expression is clear to you, that decrease in available energy is equal to T naught into delta S dash minus delta S. Answer this question. I want others to answer whether you have followed or not followed. Okay. The decrease in available energy. See, what was the available energy earlier when the heat was at a temperature T? What was the available energy? When the heat was at a temperature T, the available energy was Q minus T naught delta S. When there was a finite temperature difference and the heat was now taken to a temperature T dash, which is lower than T, then what was the available energy? The available energy became Q minus T naught into delta S dash. So what has happened to the available energy? So the available energy is now decreased from available energy 1 minus available energy 2, or available energy minus available energy dash, which becomes equal to T naught delta S dash minus delta S. Okay. So need to be clear that there is a decrease in available energy. There is a destruction of exergy because of why is the energy being destroyed? Why the exergy has been destroyed? The exergy has been destroyed because of irreversible heat transfer. And what is the irreversible heat transfer? Irreversible heat transfer is the heat transfer to the finite temperature difference. Okay, is this clear or no? I hope it is clear to all. I'm sure it is clear to all of you. So let me ask you, if it is clear to you, if it is clear to you, I am just look at the figure and I am using a different paint. I'm using a yellow now. Okay, I'm using a yellow now. What has happened? Just a minute. Sorry. So let me, this yellow hatched line, I hope it is clear to you, visible. The yellow hatched line, which is, let us say, C dash E G, okay, whatever you name it, that is not important. The area C dash E G, what is that? What is that? What does the figure C dash G E indicate? What does the figure? No, not, it is not that way. Target is not that way. Gautami, it is increase in, yeah, Gautami, you are right. It is increase in unavailable energy or decrease in available energy. Gunjan, it is difference of unavailable energy in both the cases. Right. But what does that mean? It means that that figure, that hatched line which I drawn, that represents the increase in unavailable energy or decrease in available energy because of finite temperature difference heat transfer. Okay, the area C dash EG represents an increase in unavailable energy. Increase in unavailable energy or corresponding decrease in available energy or corresponding decrease in available energy because of the irreversible heat transfer, because of the irreversible heat transfer. Is this clear? Is this clear that this hatched portion is the representation of increase in unavailable energy because of irreversible heat transfer, or the hatched portion is the decrease in available energy because of irreversible heat transfer. So please note that whatever is the decrease in available energy would be equal to increase in unavailable energy. Is this clear, Gunjan? Gautami? Gunjan, Gautami, is this clear? Okay, thank you. So, anybody who has not understood this, the usual students, apart from the usual students, anybody who has not understood this, if you understood, I would go to the next topic. But anybody who has not understood this, whatever I had discussed, all of you understood? Anybody from this 100 students who are attending these classes, whether of these 100 students, 105 students, anybody from you who hasn't understood this? Okay, so should I assume that you have understood and proceed? Okay, so I'm assuming that you understood, and let me take a small numerical based on this. Okay, so write down one numerical which was asked in some exam. Okay, some university exam. So write down this. Heat was transferred from the source. Heat was transferred from the source. Heat was transferred from the source at 1500 Kelvin. At 1500 Kelvin. 1500 Kelvin to the system at 450 Kelvin. To the system at 450 Kelvin. I will also write it down. Heat was transferred from the source, which was at 1500 Kelvin, to the system at 450 Kelvin. Okay, and the quantity of heat was heat of, let us say, 225 kilojoules per second. Okay, was transferred from the source without any heat loss. Without any heat loss. Without, so heat loss is zero. Without heat loss. Okay, without heat loss. So you need to calculate. You need to calculate what is the available energy of the source, available energy of the system, what is the decrease in available energy because of irreversible heat transfer, and what is the increase in unavailable energy because of irreversible heat transfer. So solve this. Assume the dead state temperature to be 300 Kelvin. Assume the dead state temperature to be 300 Kelvin. Okay, the surrounding temperature is at 300 Kelvin. Surroundings is at 300 Kelvin. Solve. So let us say that this is a system and there is a source. There is an irreversible heat transfer at the rate of 225 kilojoules per second, right? And we say that the system remains at 450 Kelvin and the source remains at 1500 Kelvin. 1500 Kelvin. Okay. And the dead state temperature is 300 Kelvin. Okay. So the available energy, how do you find the available energy of the heat which is at 1500 Kelvin? So we need to assume that this heat is supplied to a Carnot engine. It's supplied, we need to do a thought exercise, and it's supplied to a Carnot engine, okay, which is operating between the source temperature, which is 1500 Kelvin, and the dead state temperature, which is at 300 Kelvin. The Carnot engine is operating between 1500 and 300 Kelvin, and this Carnot engine is given the heat 225 kilojoules per second. Okay, so this will give you the available energy of the source. Then, how do you calculate the available energy of the system? Available energy of the system, which is at 450 Kelvin. So again, we need to assume that this system operates between, this system supplies the heat to a Carnot engine, which operates between the dead state temperature 300 and the system temperature 450 Kelvin. Okay, and because there is no heat loss, so same amount of heat is available, is being supplied to this. So that will give us the available energy of the system at 450 Kelvin. Okay, 450 Kelvin. So let me see what answers you have given. So Gargi has given some answers. Gunjan has given some answers. Nikhil has given some answers. Deepalakshmi has given answers. Raju has given answers. Ganesh has got the answers. So all of you are getting these answers, I guess. So is it 180? Is this calculation of 180 and 75? Okay. So let us say that this is 180 and this is 75. This is 180 and this is 75. So then what is the decrease in available energy? The decrease in available energy would be then the difference between the two. Difference between the two. Right? Difference between the two. Right. So I hope it is clear to you now. Suppose you are required to find the entropy change. What is the entropy change of the source and what is the entropy change of the system. So calculate the entropy change of the source and entropy change of the system. Entropy change of the source and entropy change of the system. So what would be the entropy change of the source? So the entropy change of the source would be Q by T. And what is Q? Q is 225 by T. And what would happen to the entropy of the source? The entropy of the source would decrease. So it is minus Q by T. Minus Q by T. So this would be minus 225 by 1500 is how much? 225 by 1500 is how much? Entropy change of the source. Okay, correct, Tanya. It will be minus 0.15 kilojoules per kg Kelvin. Kilojoules per kg Kelvin. Okay, what would be the entropy change of the system? What would be the entropy change of the system? What would happen to the entropy of the system? Whether it would increase or decrease? So entropy of the system would increase. Okay, and what that would be again Q by T, because we are assuming an isothermal heat transfer. Isothermal heat transfer, it is 225 by 450, right? The Lakshmi is correct. So it is 0.5, 0.5, okay, 0.5, 0.5, right? So what would be the overall change of the entropy? Overall change in the entropy. So delta S would be minus 0.15 and delta S dash would be 0.5. Okay. So delta S dash minus delta S T naught into delta S dash minus delta S would be what? Would be T naught is 300 into 0.5 minus 0.5 minus 0.15. Okay, 0.5 minus 0.15. Okay, so that is, what would be that? $105, right? So this way you can solve the numericals. Okay, I hope that once it is clear to you the concept. So please note that what we have discussed today. Is this clear, the numerical? Okay. So please note that when we are solving the numericals, we need to be very clear on the concepts of available energy of the source, available energy of the working fluid which is accepting the heat at a lower temperature, and we need to be very clear that if the heat transfer is irreversible heat transfer, meaning is very simple. By irreversible heat, all the heat transfer phenomena in practice are irreversible, because for the heat transfer to happen there has to be a temperature difference, you know that. But an idealized version of heat transfer, which is a reversible heat transfer, is that the temperature difference between the source and the working fluid is negligible. Okay, so if the temperature difference between the source and the system is negligible, okay, working fluid is negligibly small, then you would find that the Exergy destruction would be small. If the temperature difference is large, the Exergy destruction would be more. Okay. So our attempt should be that we need to make sure that, for example, this problem you can solve again by assuming the system to be at 1000 Kelvin. Okay. We had solved this numerical, so you can do a thought exercise. Take the same value. For example, a source is at 1500. The heat transfer is same, that is 225. Okay, and instead of the system being, what was the temperature? The system was at, sorry, 450. So instead of the system being at 450, you can take the system at 1000 Kelvin and calculate what is the exergy of the source, what is the exergy of the system, and what is the decrease in exergy, that is decrease in unavailable energy. You will find that in the case 2, suppose I call this as case 2, you will find that the decrease in unavailable energy has been reduced as compared to case 1, And why is that so? And why would that happen? Why would that happen? If you and look at this, the heat loss is there is no heat loss, the heat transfer is same. Okay, so why would that happen? That would happen because you are decreasing the irreversibility. We are decreasing the irreversibility. Okay, if you do the case 3, wherein again you take the same heat value. The source is at 1500 Kelvin. The system which is receiving the heat is at, let us say, 1400 Kelvin. Okay, and the heat transfer remains the same. So you will find that the case 3, the decrease in unavailable energy, case 3 decrease would be less than case 2 decrease. Okay, and this would be less than case 1 decrease. So which case is better? Which case is better? Case 3, case 2, or case 1? Which case is better case? Yeah, Gautam, you are right. Which case is the better case? Gautam is right. Anybody else? Which case is the better case? Case 1, case 2, or case 3? Deepak, Nikhil, which case is better? Gargi, yes. Which case is a better case? I want the students to answer this. Because if you are able to appreciate this, then and then you will be able to appreciate what we have been discussing, okay, so long. Which case is a better case? Case 1, case 2, or case 3? In all the 3 cases, the heat loss is 0. In all the 3 cases, the heat loss is 0. So whatever is the heat transferred from the source, the entire amount of heat goes to the system in all the 3 cases. Chadabari is right, Garge is right, Gautam is right, Nikhil, Deepak, Kunal, Gunjan, Tanaya, Neha. Which case is a better case? Right. What you are writing, Garge, increase in unavailable energy with a formula मध्ये केल्यामुळे delta H value. I have not followed your question, Gargi. The formulas you forget, just look at it from the conceptual angle. You will get the formulas right. So please note that if you decrease the temperature difference between the system and the source, right, then the quality of the energy is degraded less. We are interested in seeing that the quality of the energy is degraded less. So in order to ensure that the quality of energy is degraded less, we need to make sure that the temperature difference between the source and the working fluid which is accepting the heat is as minimum as possible. That would give you better results, better output from that engine. Okay, so that is what is the insight which we get from the Exergy analysis. Okay, so I hope that you are understood that if you transfer the heat without any heat loss, I'm underlining this word, without any heat loss, even if you are having zero heat loss, but if you are transferring the heat through a finite temperature difference, the quantity of the heat remains the same, but the quality of the heat degrades. The quality of the heat degrades. Okay, the available energy decreases, the exergy decreases, and this exergy destruction, this decrease in the unavailable energy is the because of irreversibility. Okay, I hope this is clear to you. With this note, I am ending this webinar. Thank you very much.